Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Camera Tuesday, we're going to talk about CCD versus CMOS. So let's dive deep into it. Now, what we are talking about? We are talking about digitization. That's it. So same way I have talked about the audio part of video basically, and audio is a continuous infinitely high resolution signal, meaning you can keep increasing your sample rate, you can keep increasing your bit depth. At some point it will just become blah, but you can keep doing that because signal is continuous and infinite. So same goes here, like signal is smooth and continuous, and I'm talking about light as a wave function, meaning these puppy. So it's kind of like you can keep slicing it, meaning if you're like, hey, how many colors can you render, you'll be like, what if I render 16,000 colors? Sounds good, but here's the, can you go more than that? Easily. What if like you go even more than it? Easily. You can keep going till infinity, it will not run out. It's a smooth continuous system. So that's the fundamental data. Now we have to plot this puppy in 3 dimensions. What does 3 dimensions mean here? 2 dimensions are for X and Y. That gives you your spatial resolution, meaning how basically how much area you are capturing. And then you have time as in frames, that gives you temporal resolution. So these 2 puppies combine, temporal resolution and spatial resolution, gives you 3 dimensions of data. Compared to audio waveform, audio waveform is just 2D. Basically, it's just a signal moving through time. Here is signal moving through time on multiple locations, so it's a 3 dimension. So frame per second is your temporal data point, but each pixel itself, like you zoom down to a data set where it's like, okay, this is a digital file. Where do I get the quality of it? That's on pixel level. So, spatial resolution already figured out, that's X and Y. But if you zoom into a pixel, then you can tell the difference between what is the quality, basically like ISO, dynamic range, noise. These happen on a pixel level. So that's the primary reason why you can have a system where you're like, mobile's 8K will be garbage compared to a full frame 4K. Why? Even though spatial resolution is supposed to be higher on mobile phone, it's fundamentally not, because quality of the pixels are lower. So quality of pixels matter here. Now, what are we doing this? Like, how the heck we are just taking light and converting it to electrical signal? In microphones, that's the microphone's job, right? It physically moves, changes something, either changes capacitance or creates a magnetic field, changes in magnetic field that creates a signal. What's doing that here? Well, thankfully we have silicon. Now, if you know about anything about silicon atom, if you have silicon atom at ludicrously high purity, like I mean pure AF, as in like 99.999, like ludicrously pure, this starts to act as a converter, meaning if photon comes onto it, bams. Photon drops, it's like bams, electron. Basically, fundamentally, it takes photon as one packet, charge packet of energy, converts it into electrical charge packet. Fundamentally, on a basic level, on an atomic level, it is the part that's doing the conversion. Everything that we do is based on this puppy. Silicon takes photons, makes it into electron charges. Now, can we use other elements? Absolutely. But this element is our favorite simply because we know how to deal with this. Another is the response curve perfectly matches of what we need. For example, can you capture ultraviolet? Absolutely. Can you capture infrared? Absolutely. But here's the, can you see it? No. So for that reason, we are trying to focus something above 400 nanometers to below 700 nanometers. That's the sweet spot. Now be mindful, silicon does extend, especially to infrared, does go somewhat in infrared, does not go that much in ultraviolet, but does go. And depending on your requirement, let's say you are building something specific, you will be like, hey, I need to see ultraviolet used for missile guidance system, you will change the element. You're like, hey, I want like for deep space observatory infrared, you may want to go in infrared, you will change this element. But that's the fundamental level. On a core level, we are selecting an element that is acting as our converter, whereas like element is like, I got this, I got the photon, I'm gonna give you out the electron. Our job becomes to convert that raw analog electron cloud and all that into digital signal. So that's the part of digitization. So we start with charge coupled device, CCD. This puppy is ancient, as in like 1970s ancient. So metal oxide semiconductor. It was very early semiconductor technology. We figured this puppy out. Now, one of the most amazing aspect of it is that it triggers, basically initiates, or like what you call flush, all this in one instance, meaning a whole sensor, X and Y, all of them gets triggered in one instance. So it has what we classify as global shutter, meaning it's not going reading one line by line, it's global. And what does it do after that? Let's say these blue parts are the silicon. it converts your photon into your useful electrical charge. What do you do after it? Let's say you triggered it, it captured everything. What do you do after it? After it, you have charge. Like all these cells have charge. You have to carry the cell. Basically, you have to handle the cell one step at a time. Now, you will first move it from the basically sensor to shift registers. Then shift register, brick by brick, tuk, 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 you will move into the final column. Final column will tuk, 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 move it out. And then you will have the true digital signal that will be converted like this, utilizing a digitizer at the other end. And digitizer will know the clock signal and the syncing speed, so it will know where to put the data in X and Y. So it does work. Now, inherently, this should tell you, like, if you are doing this many steps to convert a charge into signal. Now, be mindful, charges are very finicky, so to say, but they are charged. That's what you're supposed to do. So you are carrying forward all of this. Fundamentally, is a slow process. It is. That's why if you have a CCD compared to the same generation of technology in CMOS, CCD would be slower. Meaning, how much FPS you can get out of these fundamentally is limited by this hassle it has to do. Now, yes, there may be some research project where this row could be bypassed. You could have all that many what we call electronics right there. It could speed it up, but so far that's not the common way of doing it. So it can the steps is charge creation from photons, then it gets amplified on the pixel level, then it converts to the line, it becomes voltage, and voltage gets to digital signal. So you have so many steps happening after the signal has been created. Signal is created, signal is transferred, then you do all that hassle, basically convert it into what we call voltage, then convert that voltage into digital signal. It's fundamentally complicated system, and it is power hungry because it has to do so many steps. And this is the easiest way to describe it. It literally shifting electron one cell at a time. So you can see you took it. Basically, you have 3 units. Each units can get either positive voltage or 0 voltage. So you start with 0 volt. You absorb everything, absorb photon, you add positive, it creates an electron attraction, then you switch the positive to the second cell. Now it distributes, then you shut this off, it coagulates here, and then you repeat the cycle again. You start it on, dilute it, concentrate it, move it, dilute it, concentrate it, move it, dilute it, concentrate it, move it. And if you have 2 megapixel sensor, calculate how many times you have to do that. And I'm genuinely shocked that we figured this puppy out in 1980s. However, this is a power hungry step. You can see that, like, it's shifting charges brick by brick. It's fundamentally energy consumption. So that's why, like, in early 2000s digital camera, even though they were using CCD, they were so like brutal on batteries. Fundamentally, it's a power hungry system. However, because you are moving with charges, you do have a lot of control in analog domain, meaning at the signal level, you can do a lot of analog processes, which again may not be desirable or may be awesome for you. Depending on the use case, that may be like shut up, take money, or it may be like who cares. It can be done. However, all that thing combined, it still has better signal to noise ratio, meaning if money is no object and you do not need temporal resolution, meaning you do not want, like, thousands of FPS, still has genuine use cases. Now, when you look at this, it looks complicated. It is. This is a basically electron microscope photograph of that video linked down below, where you can see this is one active basically pixel. What is pixel? Basically, whenever you see pixel is this size, it's a half unit, meaning incomplete data. They will give you length and width and divided by the pixel. Okay, that gives you the square, but here's the deal, that's not the true pixel. True pixel is only a small area in that. Now, why is that? Well, all these things also have to be there. The wiring, the electronics, the charge capacitor, all of that has to be there. So you have a pixel, and then you have what we classify as active area. This is the primary reason why we have to add what we classify as micro lenses on top of this sensor array. All sensor array has micro lenses. Micro lenses primary job is to try to focus the light that is falling on the pixel into active pixel. Now, like, this is classified as what we call fill ratio. So this has fill ratio of 33%. That means if this is let's just say 1 pixel is 1 centimeter square, only 33% of it is actual silicon that is converting the photons into electrical signal. That electrical signal that is being converted. So it does have good signal to noise ratio, but fundamentally it's a very, very messy thing and slow. If you want high FPS, yeah, God help you. So this is charged coupled device. But it does work. Like, this is quite amazing that it can physically move charges from point A to point B. So signal quality is genuinely good. If you know what you're doing, especially if you have cooled sensors, good. So this is charged coupled devices. Then we come to CMOS. CMOS is complementary metal oxide system, so to say. And this, somebody figured it out, like, charges, while they do work, they do have their advantages. What if we convert charge into voltage not signal, digital signal, but voltage directly on the pixel level itself. That will make it super quick, super efficient. So that's what we do. This is the diagram. When you see you have way too many MOSFETs, that's the whole point of it. You have pixel that is absorbing photons, then it's getting amplified, converted into voltage signal, and then dumped into X and Y coordinate. It works far more efficiently. Signal can be transmitted much more reliably, much more quickly, and it's like exponentially faster. On a like pixel level, it's faster. But it does come at a side effect. Because of this many steps, it does have what we call rolling shutter. It literally reads row by row. So it creates a scenario where you're moving something fast. It's supposed to look like this, but instead it will look like whoo. Even on a small sensor, especially if you're moving on a fast train, you look at a mobile phone, if you see electrical poles, they will literally look bent. So that's the reason, rolling shutter. However, some use case, especially in machine vision, you may be like, hey, that's not acceptable. Like imagine feeding that rolling shutter data to your basically AI, car driving AI. AI would be confused. It's like, why the hell things are going lol? It's like, and be mindful that lol is directly proportional to your speed. So as the car speed increases, your car shapes, it will literally change. So fundamentally, that's not a go. That's like, no. Same goes with machine vision used in factories. It's like, no. For that reason, we have this puppy. This puppy puts a small charge capacitor. Basically, this is a photosensor, you put a charge capacitor. So what you do, you trigger all the photosites in one go, exactly like how CCD does. And once you close it, like, okay, I have captured the image, then you dump all the charge from basically your pixel into the capacitor, and capacitor is being read one by one, samely exactly as older system, but your capture is global because you captured everything in once and dumped everything to the next pixel, next capacitor, storage capacitor, and then capacitor is being read out brick by brick. So it's much what you call, it gives you global shutter, desirable for machine vision applications or where you need high basically your temporal resolution needs to be high quality. You have to use this, but it does create a side effect. Because of this storage capacitor needs to be on pixel level, it fundamentally reduces your pixel size, exactly how we had CCD. So you can see that like this will be the pixel would be huge and the tiny area would be the actual sensor, because it has to create the etching process, has to etch capacitor exactly there. So it does reduce your sensitivity. So if you go to Sony and be like, hey, I want like this is the sensor size, I need global shutter one, I need one non-global shutter, rolling shutter, and both could be monochromatic if you want absolute signal quality. They're like, awesome, but here's the deal. Sony themselves will tell you, it's like if you choose global shutter, it will give you at best 14 stops of dynamic range. You choose rolling shutter, it will give you at best 16 stops of dynamic range. Now for most scenario, people prefer like, you know, better signal to noise ratio. Be mindful, pixels will be physically larger, so they're like, hey, you know, I can deal with rolling shutter. So that's why we are stuck with rolling shutter. We know how to make global shutters, we just don't, because it fundamentally reduces your quality. So imagine if Sony made a mirrorless camera that had you know, global shutter, people were like, Canon looks better. Nobody was gonna care about that unless you need that. For example, how Red figured it out. They have a APS-C lineup. They're like, hey, what if people are using music videos and they need global shutter? That's why they released it. So it does allow super fast readout. Because of this structure, the fact that it's creating voltage on a pixel level, it's super easy to read out. And it also allows area selection, meaning whenever you're talking about CCD, you have to read the whole sensor at one go. It's like read, read, read. Here is like, what if don't read the whole thing, only focus on the, let's say, core part. And this is desirable. That's how you have what we call electronic image stabilization. Let's say you take a GoPro, you have a huge sensor. Now 4K footage inside that would be a smaller area. So what camera will do, it will take one photo, okay, it will read data from gyroscopes and it's like, hey, gyroscope is saying you have to move, counter move this much in this direction. It will read only that pixel. So it's like that area, this area. So in large pixel, large sensor, it can move a small box around and very high speed, as in like as high as your FPS is. So if you are running at like 120 FPS, it can keep moving it 120 times electronically. So it's much more elegant, so to say. So super fast readout, and this also gives you the ability, especially in high-speed cameras, where it's like, hey, what if I reduce the resolution? Your FPS goes up. That's the prime reason. You are selecting the readout area. You can do all of these fancy things. It basically gives you vector. It's like, hey, spatial resolution can be compromised for temporal resolution, which for high-speed cameras, it's like, shut up, take money. So it can be done. On top of that, because of the technology of CMOS, it allows what we call on-sensor technology add-ons, meaning if you know, multiple sub read arrays. That's why multiple analog to digital converter, so it can read much faster. Stacked sensor, it has analog to digital converter right there, so voltage signal gets converted very quickly. It improves your readout to such a point where it's like, do you really need global shutter? Actually, you do need it, because it removes all the issues. This is like close. Global shutter is like, don't ask about it. So that's what we can do. And again, this is the primary reason why mobile phones love it, because they can put all the digital processing signal directly on the silicon. Like, you have the silicon, behind that is the processing signal. So the final output is raw data that is in digital domain, which can be easily converted by the processor or SoC. So companies are like, especially for mobile phones, shut up, take money. So it does support all of that. It does have very low energy consumption, be mindful, because it's converting on the source, it's super low energy consumption. However, the signal to noise ratio, it's poor. It's not bad. It's like, it's poor. Meaning, if you do not have to worry about money and you're like, hey, I'm going to give you $10 billion to make a sensor and $10 billion to make a sensor, which sensor will give you better output, CCD or CMOS? CCD will give you better signal to noise ratio if money is no object. So realistically, 99% of the time you will always choose CMOS. If you can choose, you will choose global shutter CMOS. And I do expect this to come down to basically mere mortal interchangeable cameras, hopefully. Be mindful, all companies have that. Like Canon also has it, and Sony also has it. They are right now selling all these puppies to industrial equipments, not to consumer, but I do expect them to come down eventually. So that's the CMOS technology. So how do we make selection? Well, selection starts with the basic thing, base of everything. Budget of the target audience. The target audience can spend it. Like, there was a CCD based camera, cinema camera, that was so expensive it can only be rented. Yes, it was same price as IMAX camera, and Superman Returns was shot on that. Like, they had 3 CCD. The color quality was like, damn. Like, it had a feel to it, like genuinely wow kind of feel to it. So if money is no object, people will generally prefer CCD. Temporal resolution is needed, then you are forced to choose CMOS, because again, if you are building Phantom or Chronos, CMOS is the only way, because it does allow you to convert those things, meaning spatial resolution can be converted into temporal resolution if you want to. For high-speed camera, that is compulsory, so they stick with that. But if money is no object, let's say you have blank check of NASA, then you will be like, hey, I don't want CMOS garbage. I want CCD quality. This is the basically Hubble telescope's replacement. That's not James Webb Space Telescope. Hubble's replacement is built in exactly the same chassis as Hubble is. CIA apparently had a spare satellite, spy satellite laying there with a mirror completely built. Yeah, apparently CIA has a budget for spy satellites, and they have Hubble laying around. So second one is being built. This is a sensor, and each of these units, and you can easily see it, like there are 3 unit stacks in one row, and there are 6 columns. Each of that puppy is 4K, 4K by 4K. They are square, 4K by 4K, and it's high quality, basically CCD. Now I'm reasonably sure it must be cooled as in like deep space cooled, not cryo cooled to absolute zero, but cooled, and the signal to noise ratio would be awesome. And again, this is a observatory sensor. It fundamentally has the luxury of time. Basically, it's like, I'm gonna open my exposure, gonna capture it for seconds, or maybe even minutes, or maybe sometimes days. So for that reason, highest quality is needed. So CCD is like, shut up, take money. And I'm reasonably sure this is not from silicon. It does have different structure used specifically for that. Now be mindful, compared to Hubble telescope, Hubble has this size CCD. I'm pretty sure either Chinese or someone must have insulted NASA's engineers, like, oh, Hubble is tiny, Hubble is tiny. They're like, no, I have big sensor. And the main mirror diameter is exactly the same as Hubble, because again, laying over spy satellites apparently. So I'm pretty sure somebody must have pissed them off. It's like, this is huge, man. And like, each unit is 4K. So if money is no object, most of the time you will choose CCD, and CMOS can be take care of rest of the things. Like, most of the time you don't have to worry about it. However, there is one extra option for broadcast camera, specifically if you are touching 8K, is that 8K, it becomes such a hassle to do at high temporal resolution that dithering algorithm, basically extracting color data out of it, becomes such a hassle that is like, hey, might as well put 3 CMOS and get just raw data out of it. And be mindful, these things have global shutter. Requirement is basically, now you have advertisement board that gives multiple advertisement from the same camera, and person will looking there, like physical person available in the field will like, hey, there is one, let's say Hulululu ad, and the camera would be like, okay, Hulululu ad is channel number 1, channel number 2 has this app. Yes, it can do the same thing because it has global shutter. It's syncing at super duper high speed, as in like 250 fps. So it does require global shutter, does have 3 sensors, so all color data is created very quickly, and this allows you to have that high speed recording continuous, as in like these can easily record at 120 fps continuously, broadcast to a server. So whenever you see cricket match and everything is like slow down, it's like, how did they decide when to slow down? They did not bother with it. They're just recovering everything, dumping into a server. If a person at the like broadcast station is like, hey, let's rewind it, then they'll like rewind the 120 fps footage to, let's say, 30 fps. It can be done. Like, again, depending on your requirement, you need high color accuracy, you need high spatial resolution, put 3 CMOS global shutter. So selection is up to you, but this is a big sensor. So this was my presentation on CMOS versus CCD. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.